Hello, I am here today to talk to you about how to do the calculations that are necessary for the ideal gas law lab that you are going to be doing in that first week. Dr. Sanders showed you a video of 3 different experiments that were done, and she ended up getting some data that was similar to this data over here. And what I want to do is take this data and work through that set of problems so that you can figure out how to calculate the value of R, the ideal gas constant, for this experiment. And so we're going to be using the ideal gas equation that says PV equals nRT, and we are going to try and find out what that value of R is. It's a constant, and we want to know what that constant is with the units liter atmospheres per mole Kelvin. All right, so we're going to need to know what the pressure is, the volume, the number of moles of gas, and the temperature in order to calculate R, right? Because R should be equal to PV divided by NT. All right, I don't want to start with pressure because that's one of the more difficult ones for this particular experiment. So I'm going to start with the volume here, right? So we determined that the volume was 35.8 mils. We need that in units of liters. And so this is an easy calculation. It's a simple conversion. What I'm going to do is I'm going to multiply this value by 1, right? We do know that 1,000 milliliters is equal to 1 liter. And if I divide both sides by 1,000 milliliters, we can see that this side of the equation is equal to 1. And so what I'm going to do is multiply this by that value of 1, where I'm just going to convert the units. So 1 liter divided by 1,000 mils, so 35.8 divided by 1,000, the milliliters will cancel out, and I'm left with 0.0358 liters of the hydrogen gas that was collected. All right, so again, that was the simple one. The next, probably easiest one is the temperature, and the temperature needs to be in units of Kelvin. And we have units of degrees C. In order to convert to Kelvin, we're going to add 273.15 degrees Celsius, and that will get us to Kelvin. We end up with 293.25 Kelvin. Let me talk a little bit about significant figures here. This 20.1 degrees Celsius has 3 significant figures associated with it, but when you are doing addition and subtraction, the number of sig figs can change. And so when we add this that has 5 significant figures to it, we can keep all those digits in there. However, that last 5 out here is not should not really truly be there. And the reason for that is because I don't know if this is 20.10 or 20.12. I don't know what that last digit would be out there. And so I can't say that this is a 5. It might be a 7. It might be a 5. It might be a 6. We don't know. It could even be a 4, right? And so I will keep that there for all of my calculations, but I have to recognize that there are 4 significant figures that really should be here, not the 5 that I'm showing, right? Because I can only be certain out to that 2 as far as the number of significant figures is really concerned. Now, I'm not really going to worry about that too much because this will have 4 sig figs, but we've already done this one. That one's only got 3 sig figs, and so my final answer can't be more than 3 sig figs. When I'm doing multiplication up here, I have to go with the lowest number of sig figs. So I'm stuck at 3 sig figs at the most. All right, so that's temperature and volume. The next easiest one is probably the moles. And so for that, we need our balanced chemical equation. And we have up here that the magnesium is reacting with the HCl and creating magnesium chloride and hydrogen gas. I need a balanced chemical equation. That's a pretty easy one to balance. All I do is put a 2 in there and it is now balanced. The chemical equation does not say that 1 gram of magnesium creates 1 gram of hydrogen, right? The equation says that 1 atom of magnesium will create 1 molecule of hydrogen, or it will say that 1 mole of magnesium will create 1 mole of hydrogen. And again, we can't measure atoms very easily, so we're going to work in moles here. And so I don't have moles of magnesium, but I do have grams of magnesium, and I can convert from grams of magnesium to moles of magnesium using the periodic table. And the periodic table here says that magnesium, and I'm looking way over here at my periodic table, 24.305 grams of magnesium is the same as 1 mole of magnesium, right? And so now I've got moles of magnesium. Grams of magnesium are canceling out, and I've got moles of magnesium. I need to cancel out the moles of magnesium, so I'll put moles of magnesium on the bottom. I want moles of hydrogen on the top, and my balanced chemical equation says that 1 mole gives me 1 mole. When I do this calculation, the moles of magnesium cancel out, and I get 0.00141 moles of hydrogen. All right, so I've got that one, that one, that one. All I need is the pressure. And again, this one's a little bit tricky, but let me talk you through how we're going to get our pressure here. Envision for me, if you will, a pool of mercury in a big jar. And what I want to do is I want to take a glass tube that is sealed on one end, and I want to pull all the atoms and molecules of air out of that tube. So it's completely evacuated. It is a total vacuum. I then stick that tube upside down into the mercury, and because it's evacuated, what's going to happen is the mercury is going to get pushed up into that tube by the atmosphere pushing down on that mercury and pushing it up into that tube. It turns out that no matter how big this tube is, that the height of that mercury will only go as high as the atmospheric pressure is, right? So the more you can push down on here, the higher it'll go. But at 1 atmosphere of pressure, what we find is that the height of that will be about 76 centimeters. If we're measuring that, that's probably about this high, right? It's 3/4 of a meter. And so 76 centimeters is 760 millimeters, and that is equal to 1 atmosphere. Why do we use mercury when we know that mercury is poisonous to us? Well, what liquid would we use instead? We could think about using water, and if we were to do the same experiment with water, what we would find is that we would need a tube that is over 30 feet tall in order to measure how high that water is going to go up. The water is so much less dense than the mercury that when you're pushing down with atmospheric pressure down on this water, it will go much, much higher because it is far less dense than the mercury is. And so it doesn't make sense for us to use water because it is just way too, way less dense, and the column would be way too tall. So we use mercury, all right? Now there's another component to this, which is tricky. Actually, let me do that first calculation. I have 29.73 inches of mercury, and I'm going to need to convert inches into millimeters. And so in order to do that, I do know one conversion that says 2.54 centimeters is equal to 1 inch. So the inches cancel out, and I also, if I wanted in millimeters, I know that there are 10 millimeters for every 1 centimeter. And so now when I look at this calculation, the atmospheric pressure, doing that calculation, I get 755.14 millimeters of mercury, all right? That's still not at atmospheres, but I can get it to atmospheres, but I'm not going to do that quite yet. And I'll show you why momentarily. But we're almost at 760 millimeters, which means that the pressure that was measured that particular day at that particular time was very close to 1 atmosphere of pressure. All right, the last piece. All right, so if you were to do an experiment, take an ice cube out of the freezer and let it sit on the countertop. What's going to happen? First thing that's going to happen is it's going to melt, turn into a liquid. But if you were to sit around and wait, come back the next day, what you're going to find is that water is gone. Why? Well, everyone knows it's gone because it evaporated. What does that mean? It means that it has gone from the liquid phase into the gas phase. That means that there must have been some uh, uh, forces that the liquid water is wanting to get into the gas phase, right? And so it's creating somewhat of a pressure pushing back against the atmospheric pressure, right? And it turns out that the higher the temperature of that water, the faster it's going to evaporate, the greater its vapor pressure is pushing against the atmosphere, right? And so if you're at 0 degrees Celsius, is the vapor pressure zero? No, because in that experiment, if you were to take that ice cube and let it sit in the freezer for a year and you come back, you're going to find that that ice cube is much smaller. So even at 0 degrees Celsius, that water still can escape into the atmosphere because there is a vapor pressure associated even at 0 degrees Celsius, right? There's a table that was given to you by Dr. Sanders in the book. That table shows vapor pressures of water at different temperatures. And what we see is that the vapor pressure is going up as the temperature goes up. The units that are given to us here are units of kilopascals. And so we're going to need a conversion from kilopascals into millimeters of mercury. And that conversion is that 1 kilopascal is equal to 7.5006 millimeters of mercury. All right. So we're going to look at the temperature that we were dealing with. We were dealing with the temperature of 20.1 degrees Celsius. So that means we're very close to this 2.339 kilopascals. It would be a little bit higher than that. It would be getting closer, well, certainly 2.34, probably maybe 2.4, something like that. And you can find resources that give you more significant figures than just the 2 sig figs that we're seeing here, right? So that you can find a source that tells you what it is at 20.1 degrees Celsius, but we weren't given that. So we're just going to approximate here, and we're going to use the 20 degrees Celsius value. So we're going to say that the pressure that is coming from the water itself, right? So when we did this experiment, we did an experiment where we tipped this graduated cylinder upside down, and we had a stopper in here that was sealing this up, and it allowed the water to get pushed out here, and we had a volume of 35.8 milliliters of space up there, right? But some of these molecules up here were hydrogen gas molecules, right? So lots of hydrogen gas molecules, but we had a little bit, and I'll just put it in there as a little tiny X, we had a little bit of water molecules that were up there as well, creating some of that pressure. So the pressure of the water here is going to be equal to that 2.339 kilopascals, 2.339 kilopascals, and we are going to do a conversion to millimeters of mercury. 1 kilopascal is equal to 7.5006 millimeters of mercury. And when I do that calculation, the kilopascals cancel out. I'm left with millimeters of mercury. I get from that 17.54 millimeters of mercury. All right. So what we know then is that if there's a total pressure pushing down on us of 755.14 millimeters of mercury, but some of that pressure that's in this tube here, 700, so we're pushing down with 755.14 millimeters of mercury of pressure, that's how much pressure must then also be in here pushing down on the water up there, right? And so some of that pressure is due to that pressure of the water. So what we find is that the pressure of the water plus the pressure of the hydrogen gas has to be equal to the total pressure. And so 17.54 millimeters of mercury plus the pressure of the hydrogen gas that's in that tube has to equal 755.14 millimeters of mercury. So that means that the pressure of the hydrogen gas is equal to 737.60 millimeters of mercury for that hydrogen gas. All right, and we also know that 1 atmosphere is equal to 760 millimeters. We do want it R to be in units of atmospheres, so we're going to convert this into atmospheres by saying 760 millimeters of mercury is equal to 1 atmosphere, and that gives me a value of 0.9705 atmospheres. All right, and that's for the pressure of the hydrogen gas. Now we can do our final calculation for R. Let me get rid of some of this information here. R is going to be equal to P times V divided by N divided by T, which is equal to the pressure, 0.9705 atmospheres, times the volume, 0.0358 liters, divided by the number of moles of the gas, that's 0.00141 moles, times the temperature, 293.25 Kelvin. I've got all the units that I want in there, liter atmospheres per mole Kelvin, right? If I simply do that calculation, what I get is that R is equal to 0.0840 liter atmospheres per mole Kelvin. All right, and so that is my calculated value of R. That value is very similar to the value that we would expect. If you look up the value for R, you'll find that the value is 0.08206 liter atmospheres per mole Kelvin. So 0.082 versus 0.084, not bad for this particular experiment. So give those 3 experiments that Dr. Sanders gave you in the video, send that through these calculations and come up with an average R value, and then do a standard deviation calculation. You don't need to write all that out. You can simply use Microsoft Excel in order to find out the standard deviation for that. And if you don't know how to do that, send us an email and we can walk you through how to get that calculation off of Microsoft Excel. All right, have fun.